Now, in this session, our first talk is by Professor Alexander Mednik, who is a very senior professor at the Sobolev Institute of Mathematics and Novosibirsk State University. So Professor Mednik will be speaking on spectral invariance of cyclic coverings of a graph. So Professor Mednik, I now over to you.
Krishnandu, thank you very much for introduction. It's my pleasure to be on this conference devoted to the birthday of our friend and old colleague Ravi Kulkarni. Of course, my congratulations. So today I was able to talk about some results concerning cyclic covering of graphs and their complexity. Okay, let me try to do it. Certainly, everybody knows that Professor Kulkarni is a well-recognizable expert in low-dimensional geometry and topology. Now his results became classical. They are a source for many interesting investigations in different fields of mathematics done by his students and his collaboration. Also, Ravi Kulkarni was one of the first who find a parallel between theory of Riemann surfaces and graph theory. This is a very, very fruitful idea, and now it's developed by many others. I want to touch only one side of this theory, namely spectral properties and complexity of graphs. We restrict ourselves to cyclic coverings of graphs, just to illustrate the possibility of developed methods. We present some explicit formula for number of spanning trees, rooted spanning trees, and also calculate Kirchhoff index for such family of graphs. Then we investigate some arithmetical properties of the sequences and find this asymptotic. Surprisingly, but most formula we are going to deal with can be done in terms of Chebyshev polynomials. So we are going to start with some definition. This is just a very formal definition. Maybe on the next slide, I try to draw some picture to illustrate this definition. First of all, we are going to start with some finite graph G. This graph is supposed to be undirected, possibly without loops, but also we need some multiple edges. Then spanning forest in G is uncyclic subgraph that contains all vertices of G. All connected components of the forest are called trees. A spanning forest is called rooted if every tree in the forest has a root that is prescribed or labeled vertex. Connected spanning forest is a spanning tree. There is some possibility to calculate the number of spanning trees just like n times tau or t, where t is so-called complexity of the graph. Indeed, this is some spectral invariance, and I will talk about this invariance later. To count the number of rooted spanning forests is a bit difficult problem, and we want to concentrate on this problem in the future. Okay, probably a good idea to draw something, because words are maybe sometimes not understandable, but I have to find something to draw.
Does a forest always exist in a graph?
I want to find something to draw, but I cannot find. Where is it? Well, demonstration. somebody help me how to find something to draw. Demonstration.
Is there any problem in the?
I cannot find the instrument.
Very
Oh,
most.
what is it? Some mouse, something like that.
So you are using a computer or an iPad?
No, I'm computer with me, not iPad.
Okay, so no, yeah, you just click.
Usually there is a possibility to do this. Oh. Так, так. Sorry for this. Well, very strange. Usually there is one every time. No, well, just imagine that I am able to code. This is a graph, empty graph. It has a vertices, also some edges. What is a spanning tree? This is just a tree which covers all vertices of our graph, but not necessarily the edges. Forest is just a collection of trees. Again, we suppose that together all these trees cover all vertices of our graphs. So this is a forest, spanning forest. But for some technical reason, well known for people doing combinatorics, we prescribe to each tree in our consideration a root. So every time we are talking about rooted trees and rooted forest in our consideration. This helps us to find the beautiful formulas. Counting unrooted guys is completely different problem. It's very delicate problem. It can be solved for trees, but not easy to solve this for forests. So this is just a general imagination about things I'm going to do this. Okay, let's continue. Yes, this was good. Now some more definitions. They are more related with analysis. Maybe it will be more understandable in this case. So again, we consider a finite graph without loops, denoted by V the set of vertices and by E the set of edges of such a graph. If we have two vertices, then A small with two indexes, V and U is the number of edges between these two particular vertices. The matrices formed by these numbers usually called a Genchesky matrix of a graph. By D of V, we denoted the degree of vertice. So how many neighbors has this vertex in our graph. Also, we introduce a diagonal matrix formed by these degrees and consider the difference matrix of degrees minus a Genchesky matrix. This particular matrix is called Laplacian matrix, or just Laplacian for the graph. This is an analog of classical Laplacian, which is well known in analysis in the theory of manifolds. But of course, it's very non-easy to recognize that it's guy everybody knows. I know this will be very important for us, that this matrix every time is non-negative. Some aging values of this matrix can be zero. The number of zero aging values is exactly the number of connected components of the graph. For example, this graph itself is connected. We have exactly one zero aging value of the graph. All other aging values are strictly positive. Well, that I denoted by I sub n the identity matrix of all the n where n is exactly the number of vertices of our graph, and consider the characteristic polynomial of such Laplacian methods. The eigenvalues of this guy will be very, very important for us. This is more or less the main subject of our investigation. Just to understand the nature of Laplacian, I consider just Laplacian equation. For example, we consider a function f defined on the vertices of the graph and consider the equation. Laplacian applied to this function is equal to 0. The meaning of this equation is very easy to recognize. The equation which is given on the slide is exactly equivalent to the following mean value property. The value of function in the prescribed point W0 of degree d is exactly mean value of its neighbors. Is it understandable? Mean value property, like for harmonic function in the classical analysis. Так, is it okay?
Yes,
Would
yes,
you hear me?
yes, yes.
Also, the people who are doing analysis know very well if continuous functions satisfy the mean value property in some domain, it is certainly harmonic. So this is more or less a standard definition written in some very, very strange way. Many years ago, when I saw the definition of Laplacian for the first time in the graph statement, of course, I was surprised. This is something strange. This is unusual. This is not supposed to be. But sooner or later, I understand. Yeah, this is a standard harmonic analysis, but only we are doing its discrete version. So we have a notion of Laplacian. This is a matrix, positive, non-negatively defined matrix. It's symmetric and has a very, very nice properties. Well, let me consider again the characteristic polynomial of this matrix. It has a number of coefficients. Very interesting, but the geometrical sense of these coefficients is well known. It's given by the, classical Kelmans and Chelnakov theory, which states us that absolute value of each coefficient of this polynomial coincide with the number of rooted spanning trees consisting exactly of k of the spanning forest consisting exactly of k trees. K forest, this means a forest which has inside exactly k trees. So if we are able to draw this forest explicitly and draw all of them, we are able to find the value of this coefficient in very geometrical way. I remember that all eigenvalues of the matrix under consideration is non-negative. So by Bezout theory, the sequence of this coefficient is alternating. This means that we are able to calculate the number of spanning forests in this particular way. This is a forest with one tree inside. F2 is just a forest with two trees and so on. Because of this sequence is alternative, we have the following formula, which gives us exactly the value of polynomial in the point -1 up to signs. This exactly coincides with the determinant of matrix 1 plus Laplacian. I don't know, in analysis, this is not so common. Maybe this is Helmholtz operator, maybe something similar, but usually people prefer to deal with Laplacian itself, but not with 1 plus Laplacian. But we need exactly identity matrix plus Laplacian. This result was independently obtained by many authors. I mentioned just very few names, but indeed this is just a consequence of the Kelmans and Chelnakov theory. In particular, the famous Kirchhoff matrix 3 theorem, obtained many, many years ago, told us that the number of rooted spanning trees can be obtained as the first coefficient of this polynomial. Here, tau stands for the number of spanning trees which are without roots. In the case of spanning trees, this is more or less equivalent problem. Spanning tree cover all vertices of the graph under consideration. So there are exactly n possibility to put a label on this tree. So calculate the number of spanning trees or calculate the number of rooted spanning trees. This is exactly the same problem. But it's not true anymore for the forests. So I continue. What is the subject of consideration? As I already told you, we are concentrated on the cyclic covering of the graphs, and typical example of the branch of the cyclic covering of the graph is so-called circulant graphs. For example, we consider circulant graphs with the signature 1, 3. What is the meaning of this notation? The meaning is very simple. We just start with the regular n-gon. In this case, this is 7 gons. Then we produce all diagonals of the length 1. This is just edges of this regular 7 gon. Then we also want to draw all possible diagonals of length 3. You can easily recognize each of these pictures. As a result, we have exactly the example of circulant graphs. So the main investigation can be done in my lecture for circulant graphs, but the same technique for sure can be used also for arbitrary cyclic coverings. But the results in general case, of course, are much more complicated. This is just formal definition. Circulant graphs, which are already shown on the previous picture, can be defined in the few equivalent ways. The first definition, automorphism group of the graphs includes a cyclic subgroup that acts transitively of the graph vertices. This is not exactly full group of automorphism, just subgroups. Also, the identity matrix of the graph is circulant matrix. And one more equivalent definition, the graph is Cayley graph for cyclic groups. The people doing this subject prefer one of this definition, but probably I will do with the first one. Okay, what is known in general for circulant graphs? Surprisingly, but isomorphism problem for circulant graphs was solved just very recently. This is the result of Misha Muzikchuk, former Russian, now he's working in Israel. Also, two people from St. Petersburg, Yevdokimov and Ponomarenko, proved that it's possible to recognize circulant graphs from the set of all graphs for the polynomial time. So in some sense, this is a very doable subject for investigation, but at the same time, not so easy to solve, for example, isomorphism problem for these graphs. It can be done, but not in an easy way. This is a typical example. Of course, the first example is just general situation. We have again regular n-gon and diagonal of length S1, S2, and so on, SK, drawing in this graph. This number usually called jumps. In my understanding, this is just diagonal, but the standard notation is just jumps of our graphs. Okay, the first example, of course, is cyclic graph. This is just regular n-gon, nothing more. Anti-prism prism graph, Möbius ladder graph, complete graph on n vertices, and also complete bipartite graphs. All these examples sooner or later appear in my lecture, so I avoid the detailed explanation of this example. Okay, Is it clear, this definition? Because it's basic definition for our consideration. Could I continue? Okay. Так.
Everybody is clear? I mean,
Everything is
Yes.
clear, okay?
Yes.
okay, okay.
Okay.
Yes.
Mhm. Okay, now we start with the fixed circular graph. Suppose it is a graph on n vertices, and he has a jumps S1, S2, and Sk. You can imagine just diagonals of the respective lengths are drawn in the picture. We have to introduce also circulant matrix for our graphs. Everybody knows what is circulant graphs, circulant matrix. We have to start with some sequence of number. This is the first line in our matrix. The first line can be obtained from these numbers by shift to the right. Then we have to produce one shift more. This will be the third line of our matrix, and so on. So this is just the situation when we have a shift of sequence of our number. Should I explain more or more? Less you can.
Yeah, we understand T. Yes.
Understand. Well, now we consider a Laurent polynomial, which is given by in very precise way. It depends from jumps of our graphs. But of course, there are positive and negative powers of our polynomials. Then the Laplacian matrix of our graphs can be obtained in very easy way. We have just to put this circulant matrix inside of Laurent polynomial. As a result, we have a Laplacian matrix. So from analytical point of view, this is quite easy. So this is basic polynomial we are going to deal with. Well, eigenvalues of this matrix, easy to find because circulant matrix every time is diagonalizable and its eigenvalues are exactly one primitive root of degree n from the unity and powers of the primitive root of degree n. So this means that we can just use this diagonal matrix instead of matrix T to calculate the eigenvalues. As a result, we have a full list of eigenvalues for Laplacian of our graph. They are given on this slide. Just easy combination of the primitive roots of the unity. Of course, there are n of them, and one of them, I think, zero guy is equal to 0. Then, to count the number of spanning trees, we have to use formula obtained by Kirchhoff many years ago. We have just multiplied all non-zero eigenvalues of our matrix and divide the product by the number of vertices. So this is the answer for the number of spanning trees. Well, easy to draw, easy to see, but not so easy to calculate. If the number n is at least 12 and you ask your computer to calculate this product, it will be a bit confusing. Of course, sooner or later he gives you the answer, but say, no, I don't like such kind of problems. Please find another way to calculate this number. How to do more simple calculation for this number? This more or less the result of the first theory. The number of spanning trees in the circular graph under consideration is given by the following formula. Now we have a finite product. The number of elements elements of this product are fixed. It's exactly the size of the largest diagonal, -1. Q is stands for the number of squares of the jumps, and WP is all possible roots different from the one of the following equation, which is also fixed for our consideration. T of K, T of N is the Chebyshev polynomial of the first kind. Of course, I should remember that the Chebyshev polynomial of first kind is given by the very simple formula. There are many books related with this polynomial. There are many algorithms how to calculate this polynomial. If your computer has even some very simple computer problem, it can calculate this polynomial very, very quickly. So this formula is much more simple as it was before, and also give us a possibility to calculate this number very quickly. Later, I will indicate the proof of such theorem or maybe related theorem. Now you just recognize what is inside. Inside is just Chebyshev polynomial, nothing more. It can be calculated in the root of some fixed equation, which can be solved once and for all n. Usually n, the number of vertices, is going to the infinity. And this is the main problem of calculation of these guys. So we are not able to find this big number, but very often we are able to find the asymptotical behavior for such a number. Now, I want to say something about the number of rooted spanning forests in our graphs. This essentially is a new subject. In the case of spanning trees, there are thousands and thousands of papers related to this subject. The first paper was done by Kelly, maybe by Kirchhoff itself, but for this time, of course, many results appear. Completely different situation is with rooted forests. We recognize that there are very few papers related to counting of spanning forest. So our result is given again in terms of Chebyshev polynomial. And now, in this case, it has even more simple form. The number of rooted spanning forests in the same circular graph is given by the following product. Again, we have to pass through all roots of some additional equation. This is more or less the same equation as before, but before it was 0 instead of 1 here. And now we are able to use also all roots. For sure, all of them will be different from the unity. So the formula became even more simple. Well, it's understandable, the statements of these two theorems, because now I'm going to change to the proof of the theorem. It's okay? Could I continue?
Yes. Yes.
Well, the proof, I indicate the proof of the second theory, but the proof of the first one can be done more or less essentially by the same argument. So we have the list of eigenvalues. This is the same eigenvalues of before plus 1, so we can easily recognize them. So how to calculate the determinant of the matrix 1 plus Laplace? Well, just got the product of all these numbers. We note this polynomial under consideration is symmetric in this particular way. So if z is the root of this equation, 1 over z is also root of the same equation. Now we recognize the product we want to calculate as a resultant of two polynomials, p of z and z to the power of n minus 1. Everybody knows what is resultant. Resultant. This more or less definition. You have to calculate the root of one polynomial and put this root inside of the another polynomial and multiply all possible values. Resultant of two polynomials is almost symmetric. If you interchange two polynomials up to sign, we have the same number, plus minus 1. Because I'm looking for the positive integer, I just put the modular, don't care about plus or minus is inside. Now, two polynomials are replaced by each other. I have to use this polynomial z2n minus 1 and put all the root of p inside. As a result, I have simple expression like this. One can recognize that inside we have exactly the Chebyshev polynomial. To do this, we use the standard identity, which relates the Chebyshev polynomial to polynomial z2n. Roughly speaking, Chebyshev number n is z2n is the same polynomial, but they are calculated in the different coordinate system. So their behavior is very, very simple. This is just semi-conjugation of these two polynomials. Now, because of this identity, indeed, we have the results of our theorem. One can easily recognize that new variable w is a root of the following equation. This is the main idea of the proof. Okay. Now I want to say something about generating function for these guys. If we consider again the number of spanning trees in circular graph and consider the generating function, then we have proved that this every time is rational function with integer coefficients. Moreover, it still keeps a symmetry of our polynomial. The result was initiated by our friend and colleague Sergei Landau from Moscow University. He asked us, why not to prove that this function is rational? Yes, it will be done, and also we have possibility to calculate this function very explicitly. These are some examples which illustrate our theorems. Consider the graph, circular graph with jumps 1 and 2. It's one of the possible situations. Very known result that the number of spanning trees in such a graph is given by the formula n times Fibonacci n squared. Many people prove this result independently. There are a lot of citations, but probably I avoid the citation because it's also a consequence of our first theory. As a result, if we consider generating function, we have just very simple rational function where W stands for this combination of x. More complicated case, graphs with jumps 1 and 3 shown on the first picture. It also has a rational generating function of the slightly more different structure. Okay. Now I want to investigate some arithmetical properties of the obtained sequences. In number of papers, it was noted that the number of spanning trees in the circular graphs very often has a form, number of vertices times a full square. But it's not true in general. There are some exceptions. And for a long time, it was not easy to explain this phenomenon. To do this, we recall that any positive integer p can be uniquely represented in the form q times r squared, where p and q are positive integer and q is square free. Probably you understand what a square free number. Yes, I don't need to explain this. For example, 12 is not square free. It's 3 times 4. 4 is 2 square. So square free part of 12 is just 3. Now I am able to formulate, to give a formulation for the main result about the arithmetical behavior of the sequence. Let's again consider the number of spanning trees in circular graphs. Denote by P the number of odd elements in the sequence. Easy to calculate if you know the sequence. And let Q be a square free part of P. Then every time there exists an integer sequence such that number of spanning trees is n times full square if n is odd, and number of spanning squares is q times n times full square if n is even. Q is well defined and easy calculated from the sequence of our jumps by hand. Nothing special is needed to do this. So this is more or less the understandable situation, what happens with this sequence. By secret, I should to told you that this number Q indeed can be replaced by the largest possible eigenvalues of our graphs. So this is just small secret. In the case n is odd, there are no largest number in our graphs. There are two equal, which are biggest one. In the case of n even, we have exactly one largest eigenvalue. It is exactly this coefficient. So more or less, this is explanation of this situation. For the case of spanning forest, situation as before is even more simple. Consider the number of spanning forests in our graph. Again, let P stand for the number of odd elements in the sequence of jumps. And now Q is just a square free part of the number 4 times P plus 1. Then there exists an integer sequence A of n such that in the case of n odd, we have exactly full square for the number of spanning forests. In the case of n even, we have q times full square. So now the result is much more understandable. Roughly speaking, up to some recognizable constant, every time the number of spanning forests is a full square. So these are arithmetical properties. Of course, not so easy recognized directly from the formula, but this just again comes from the analysis of spectra of our graphs. Indeed, this is more or less the idea how to prove this. Because of properties of the primitive root, we have eigenvalues of our graphs in couples. Eigenvalue number g is the same as eigenvalue number n minus g. So we have collect the eigenvalues in couples in this particular way. So the products of these eigenvalues is exactly square of this expression if n is odd, and square times the maximal possible eigenvalues if n is even. In both cases, square numbers are products of Galois conjugates algebraic numbers. Product of Galois conjugate numbers every time is positive. This is so-called norm of algebraic number. It can be negative, but every time integer number. So all numbers inside of squares are integer, and we essentially have to prove the theorem. Of course, we are able to calculate the maximal possible eigenvalues of our graph. This is exactly the number 4 times p plus 1. So the result follows. This is simple idea to prove these arithmetical properties, looking on the behavior of the eigenvalues of our graphs. Okay, is it understandable? Could I
Yes,
continue? Well, now asymptotical behavior. For simplicity, suppose that all jumps together formed a relatively prime sequence. This is not so important, but formula became a bit more complicated in the general case. Then the number of spanning trees has the following asymptotic. And still the number of vertices Q is the number of sum of squares of our jumps. What is A? A is special constant. It's given by the Fowler integral and has a special name. This is a Mahler measure of the Laurent polynomial under consideration. Mahler measure. Mahler measure was introduced by Mahler many years ago to introduce the properties of some algebraic numbers. It's easy to define in the other way. If we have a polynomial like L of Z of our case, we have to collect all roots of these polynomials whose eigenvalue of modulo is greater than 1 and to take the product of them. So this is a product of all roots whose eigenvalues is greater than 1. Very fortunately, this is given by a very simple integral. You can calculate this integral by hands or maybe by computer in very important cases, and it gives us a very precise constant in radicals or maybe something like that. Some constant will be shown later. Again, if we return back to the number of spanning forests in the same circular graphs, we have even more simple asymptotic. In this case, the number of spanning forests asymptotically is the same a to the power n, where n is again the Mahler measure of the associated polynomial. For forest, we have to use the same polynomial as in previous slide, plus 1. But the same integral should be calculated. Again, we have a very simple way to find an asymptotic. Okay, what about time? I am at time or maybe not. Is it okay?
Yes, yes.
Now another invariant, a bit more complicated. This is so-called Kirchhoff index, which was introduced by Klein and Randich from the very interesting situation. They tried to define the resistant distance between vertices of the graphs. This means that we have electric system based on our graphs. And we suppose that each edge of our graph has a resistance equal to 1. Then we are trying to calculate how it's called effective electric resistance between two vertices. There are standard way how to do this. This is standard Kirchhoff law, standard Ohm law to do. Then Kirchhoff is defined as a sum of all possible distances between vertices. The definition, a bit difficult definition, was motivated by so-called Wiener index. This is very famous in graph theory. Wiener index is defined as the sum of all possible distances between vertices of our graphs. Surprisingly, but these two notions are very connected. Kirchhoff indexes are bounded from the above by the Wiener one, and the equality takes place if and only if the graph G is a tree. So this is a more or less natural definition. But of course, very difficult to calculate using electricity scheme every time. What we have to do? Well, by two independent papers written in the same time, now we know that Kirchhoff index can be calculated by making use of the eigenvalues of our graphs. Recall that in the case of finite and connected graphs, only one eigenvalue is equal to 0. So we have to pass through all non-zero eigenvalues and calculate this number. So again, we are dealing with eigen problems for our graphs. How to find this number? Well, the first theorem. If we consider circular graphs with the same jumps as before, and looking for the formula for Kirchhoff index, then we have the following result. Kirchhoff index of the circular graph is given by the following very explicit formula. In this case, I have to use both Chebyshev polynomial of the first kind, T of n, and Chebyshev polynomial of the second kind, U sub n minus 1. The definitions are given on our slides. Well, again, n is going to the infinity. This is a complicated problem. That the number of terms in our formula is fixed. It's not so big formula indeed. This gives us a possibility to find asymptotical behavior for this index. Surprisingly, but asymptotics is quite simple things. I avoid the proof, sorry for this. This is just complex analysis, not so difficult by some argument from the complex analysis. Indeed, we use just residues for analytical functions. After that, when the theorem is already proved, we have the following corollary. The Kirchhoff index for circular graphs has the following asymptotic. We have a polynomial of degree 3 in n. Moreover, the zero. This is just polynomial without zero terms. And we have a very, very small remainder for such formula. This is exponentially small number. So polynomial of degree 3 plus very small, exponentially small remainder. Again, we have to solve some equations related with Chebyshev polynomial to find some constant inside. But usually it can be done more or less in the simple way. This constant A is every time greater than 1, which guarantees that we have indeed the exponentially small term for our graphs. The same result can be obtained for so-called graph result valency, and also for direct product of circular graph by path graph on the two vertices. This is two special families. They appear in the graph theory very often. So this is just a small remark. Now I am able to give some examples. Cyclic graph. This is just regular n-gon, nothing more. The number of spanning tree is just n. The number of spanning forests is a bit more complicated. Surprising, but it coincides with the number of spanning trees in the so-called wheel graph. Kirchhoff index, easy to find, just polynomial. Okay, now Möbius ladder graph. Kirchhoff index is given by the order 3 polynomial plus some additional terms. Here is a constant which can be calculated very explicitly. This is the result with my student Galia Bayganakova, and also independently, but a slightly different form obtained by Zinker. For the prism graph, we have a similar formula. So just example how to apply the previous result. More complicated examples. Graph with jumps 1 and 2 was considered before. We already know the number of spanning trees for these graphs. Here F is the Fibonacci number. To find the number of spanning forests, we have to solve some special quadratic equation, which was shown in the theorem number 2. It has just two roots. As a result, we have very explicit formula for the number of spanning forests, and also have a very explicit asymptotical behavior for this number. The corresponding Mahler measure of polynomial can be calculated very explicitly. This is quite big constant. Well, Kirchhoff index. In this case, we are lucky because everything can be done in terms of Fibonacci numbers. This additional term indeed is a constant, which is well known, and the remainder is given by the golden ratio. Golden ratio is not so big, but still we have asymptotically very, very small remainder in this case as well. So these two examples which illustrate all the above theorems. More complicated situation, graphs which jump 1, 3. Again, we have to solve some additional equations, but everything can be done very explicitly. We have a very nice asymptotical behavior, and this is just the constant from the remainder. To calculate the number of spanning forests, we have to use just Chebyshev polynomial of the first kind, and they calculated in some very explicit complex numbers. For the number of spanning forests, we have a bit more complicated formula, and to find this number, we have to find the root of the cubic equation. The equation is quite simple. So again, essentially by hand or by computer, we have able to calculate this number very, very explicitly. It's an interesting consequence of the arithmetical theorem. In this particular case, the number of forests every time is a full square. Of course, one can find the sequence A of n very explicitly. This is a recursive sequence. There is some recursive relation for this. So you can investigate all problems, arithmetical and the general analytical related with a very explicit way. Okay, this more or less all I want to say. This is some literature. All of these results are already published. Of course, I forgot to say this is joint results with my collaborator, Ilya Mednych, which is exactly my son, Lilia Grunwald, our PhD students, and our young collaborator from South Korea, Yang Suk Kwon. So all publications are on the list. Well, thank you very much for your attention.
Okay, so let's thank the speaker. Is there any questions or comments?
It's beautiful mathematics.
No, I'm waiting for some questions. It's quite important for me. Please do it.
Yeah.
Any question are very welcome.
I think we can have some research group in on your work in India.
Yeah.
Yeah, welcome to join us. Why not? There are many calculations we need to produce. Of course, this is just finite results, easy to see, but not so easy to find. It was a lot of paper by Chinese mathematicians in this field, but they do with graphs piece by piece, case by case, and the results for us will be a bit complicated.
How much computer do you use in your work?
We use indeed a symbolic calculations. So all formula are done by computer in symbolic way. After that, of course, we're able to find handmade proof, yes, but the first experiments are done by computer. Of course, after that, we verify all results by numerical calculation as well. Usually we use 2, 3 independent computer programs to do this, to be sure that everything is correct. Mostly we use Mathematica or Maple Nothing more serious is enough for our purpose. But at the same time, yeah.
Any of these programs like GAP or SAGE or
Yes, of course, we know all these things, but the reason is that indeed we don't need to calculate too large numbers. For small numbers, Mathematica and Maple are enough to show that asymptotical behavior is correct, usually enough and up to 100. For 100, we have a very nice coinciding with asymptotical behavior. So we are already happy to do this. But also because formula became in some sense very simple, we're able to calculate, I think, just 20,000 sometimes we tried, just for fun, it will, no problem.
Yeah, so there is a question from Vikas Jadhav. Sir, can you give some direction regarding your paper on fixed points of cyclic groups acting on graph? Because you can unmute yourself and say yourself.
What do you mean about this paper? Some reference or just?
Because can you
Yeah,
speak?
yeah. I wish to know about, are you working right now on non-cyclic groups or some other kind of groups?
Sorry, not understand.
You have your
exactly.
paper on fixed points of cyclic groups.
Yeah, I got the paper, yes.
Yeah. So are you right
You
now working
find
on
it or
non-cyclic groups or some other groups?
Or some other group. In general, yes. We have to use characters, table of characters of these groups to investigate more difficult situations. In the case of cyclic groups, of course, all characters more or less are related with the primitive rules of unity, like in my lecture. So that can be easily calculated, correct. In the case of diagonal groups, we have to use some square roots, but of course it's more or less doable. Again, this is just simple table for characters of the group. In general case, we have to use just abstract table of characters. Sometimes they're easy calculable, sometimes not, this depends, but in any case, the general result by making use of table of characters can be obtained in this case as well. I never tried to do this in more or less general ways, but for sure it is doable.
Thank you, sir.
a small query, not a question, may I?
Yeah, sure.
I mean, as Professor Kulkarni said, it's really beautiful mathematics involved in all this work. Have these ideas found applications outside of graph theory? Because that's normally the case. Graph theory finds applications everywhere in other domains of mathematics, from topology.
Application to which field? To really applied mathematics? Or
Yeah,
just
within
to
mathematics, yeah.
apply no, indeed, I never deal with true applications. Certainly there are, even I can explain where they are. They're in part of theoretical physics, and this is so-called also statistic physics. Some problems are coming from this field. We are able to calculate some important invariants, which can be used by this physicist. More or less, they are interested in asymptotical behavior. Some constants coming from asymptotics are very important for theoretical physics. There are a number of papers of guys doing this subject. Sometimes I even try to find some correct reference to them, but there are thousands and thousands of them, you know, that these people doing, well, 1,000 papers. But yes, you can apply this result partially, of course, to some questions related with theoretical physics and also with other fields. Also, another application, I forgot to say, because this Kirchhoff index coming indeed from mathematical chemistry, and for graphs coming in mathematical chemistry, very important formula which give us the possibility to calculate this invariance. So probably you can apply also this result to mathematical chemistry as well. No, at least two fields, maybe some more, I'm not sure.
Thank you.
Another application, but of course, Ravi Kulkarni knows it very well. If graphs became bigger and bigger, sooner or later it became like a Riemann surface. And all invariants coming from the graph became invariants for Riemann surface as well. It's an interesting question, but of course very difficult. For example, eigenvalues sooner or later became eigenvalues of Riemann surface itself. No, just questions, just problems for all life. But of course, interesting to find this connection as well.
You use the words mathematical chemistry. You use this word, mathematical chemistry.
Yeah, sure. Yeah.
Is it developing as a field in Russia? Or is it just your word?
I don't know mathematical chemistry. I don't know.
No, but in
a
this,
lot of journals related with this subject is not
Right.
my word. Maybe another
Sure.
combination, but general idea is the same. No. This
no, there are natural graphs in molecules,
Yeah. Graph molecules and so on. Yeah.
and so the energy of the graphs, these types of concepts are there.
You are right. Energy
Ah.
of graphs can be calculated also by making use of
Hmm,
eigenvalues of these guys.
Right.
But for energy, I did not try to find asymptotics, a bit more complicated. But energy more related with the analysis of spectrum for Riemann surfaces.
Hmm.
Because in the case of Riemann surface, we have a beautiful formula related to some sense of energy with geometrical parameters of Riemann surface. In the graph case, I don't know, it's supposed
Yeah.
to be also.
Okay, so